what we're going to do today is we're going to kind of expand on what we've been discussing, which is when reactions are equilibrium, right? And so we're going to talk today about how to shift equilibrium by putting stresses on a system, and then also mathematically how to express the concentrations in the reaction quotient, which is basically a K, when things are at equilibrium. So I'm going to, just this first slide looks like a hot mess. Like I'm going to go ahead and just I'm not even doing this right now. So SO2, Cl2, SO2, Cl2, okay? I'm just going to go and make up some stuff to make it a little bit easier for you. So what we had there is we have SO2 and Cl2, and these were both gases. And then we had SO2, Cl2. That's a gas. Okay? And so it gave me some concentrations, and the concentrations were in pressures or brackets. Brackets? On the example.
Yeah,
Brackets. So I'm writing a Kc. Why does that even matter? Because I'm writing a Kc. So the equilibrium expression for this would be SO2, Cl2, so are you okay so far? All right. Now, if I told you, now I'm just going to make up a Kc value that's easy to follow. Okay, I'm making this number up. Let's just say the Kc is 8. I realize on your screen it's not, but I'm making up an easy to follow number to make this better for you, okay? Let's just say Kc is 8. So that means that if they gave me the equilibrium concentrations, that if I were to plug them in here, I would get 8 when I did all the math, okay? So let's just say the molarity of SO2, Cl2, let's just say that the initial concentration of that was 16, okay? And let's just say the initial concentration of SO2 was 2 molar, and this was 1 molar. And then I would get, when I did the math, 16 divided by 2 is 8. So that's at equilibrium, right? You understand that? Well, you know also that a reaction, as it goes through, it doesn't automatically go to equilibrium. At some point, when you start, you have initial concentrations. And if I started out and I had, let's say at the beginning of this reaction, the concentration, the initial concentrations, if they were 4 and 12 and 11, I wouldn't get 8 when I put it in there, right? Well, what if I said at some part, I'm going to actually erase initial. It could be at the beginning, it could be any time. At some point in the reaction, I'm not telling you when, some point SO2, oops, let's just say it was some point, right? And it could be any point, could be the beginning, middle, doesn't matter. Let's say the concentration of sulfur dioxide was 4, and then the concentration of chlorine or gas would be, 3, and then the concentration of SO2, Cl2, let's just make that, let's just make that 10. Okay. Well, can I put that in? Can I say Kc equals all this? Is that right to say the equilibrium constant is equal to this? Is that ain't this? I'm not at equilibrium. I'm at some point, and I don't know if I'm at equilibrium. So y'all realize this is just dividing a bunch of stuff, right? So if I'm not at equilibrium, instead of saying K, we're going to say Q. And Q is the equilibrium quotient. Don't let that freak you out. Quotient just means what you get when you divide, right? So the reaction, when I put stuff in and divide, is Q. And it doesn't have to be at equilibrium. That's the difference. If I know I'm at equilibrium, I'm going to use Kc. If I don't know if I'm at equilibrium or not, I'm going to use Q. And you do everything the same. Q is equal to all that stuff at any point, but not necessarily at equilibrium. So at some point in the reaction, Q would be equal to, same expression, 10 divided by 4 times 3. So Q is equal to 10 divided by 12, which is like, I don't know, 80. I feel like, or point, I should say point. I'm doing math like I would be doing a grade. There'd be 0.84. Is that right? just made all that up. Is it 8333333?
Yes.
That makes me feel a little bit better. Okay, so anyway, Q is equal to 8 or 0.83. K was equal to 8. Okay, so that means, am I at equilibrium? Does this equal 8? That was my equilibrium constant. Does that equal 8? I'm not at equilibrium. You kind of follow what I'm saying? Just basically take whatever concentrations they gave you, put them in there. Can I make an ice table out of this? These numbers, if I gave you at some point in the reaction, here's the concentration. Can I put that in an ice table? No, because I don't know the equilibrium concentrations, and I'm not at equilibrium. So that E on the ice table ain't working. So this is actually, you want to cross your fingers and like hope they just give you random stuff, and you can plug it in. You don't have to make an ice table. It's easier. So let me tell you what the deal is with this. What you're going to do after you figure out Q and K, they're going to ask you, what direction will this reaction proceed? Because it's not at equilibrium, so it's going to keep going until it gets to equilibrium, right? Like that's what's going to happen. So you make yourself a little number line and always put a 0 on it because people are a little slow sometimes. I'm just letting you know. So Q is equal to 0.83. That looks terrible. I don't know what else going. There we go. I'll make it better. Q is equal to 0.83, and then equilibrium constant, Kc, was equal to 8. So this is what you do. I made it, this is not in your PowerPoint really, but just please do what I'm telling you. The reaction is going to proceed so that it gets to equilibrium. So guess what? It's going to make products. So the reaction is going to proceed in the forward direction to get to equilibrium because Q is less than K. On the AP exam, the way you'll have to justify that answer is you'll do this math, and you'll say the reaction will proceed in the forward direction to make more products because Q is less than K. You don't have to draw a number line. That's a Miss Freeman special, but it'll keep you from screwing up. Anyway, so it's always like you have to do the math and say Q is less than K, so we'll proceed in the forward direction. If we had done all that math and we had gotten Q was 10, then guess what? The reaction will proceed in the reverse direction, the reverse reaction, right? Because Q is greater than K. And guess what you're at if Q is equal to K? If they're equal, where are you at? Equilibrium. So you're at equilibrium because Q equals K. And so sometimes, especially on multiple choice tests, they'll give you some random concentrations. You'll plug them into the Kc expression, and you'll see that it equals Kc, and then you'll be like, okay, it's at equilibrium. That's a very common kind of question. But these are great. These are the easy kind of questions because you don't have to do much. The problem lies in the fact that you'll have to, in that situation, know what the heck to do. So that's not even in the PowerPoint. That was just what I was doing. So at a different temperature, right? We changed temperature. At a different temperature, Kc equals 0.042. Okay. A chemist tests the system, and at some point, does it say equilibrium? Nope. So I'm doing Q, right? SO2 is 4.62 times 10 to the negative 4th. Chlorine is 3.85 times 10 to the negative 3rd. And SO2Cl2 is that. Is the system at equilibrium? Can you do this by yourself? You want to do it real quick? Knock it out. I'll do it up here. The first thing you should do on any equilibrium question is not make an ice table. That's tempting. That's wrong. The first thing you should do is write the equilibrium expression. And I already did that, but oh, I thought I was doing something else. Oops. I'll make it go away. So we're not going to write Kc equals blah, blah, blah. We're going to write Q equals. Now, it just so happens that this reaction doesn't have any coefficients. If they did, of course, I would have exponents, right? Still did the exponents, everything's the same. Has the the magic equilibrium theory visited and is Q equal to K? It's probably not, right? But you're just going to punch buttons on your calculator. Be careful with your parentheses, right? Don't want to get these wrong because you can't use your calculator. Let it be wrong because you don't know what you're doing. Is that what you guys got? 15.7? So, is the system at equilibrium? No, because Q does not equal K. So, I mean it when I say to draw a number line. I really meant that from the bottom of my heart. So, if I draw a number line, there's Q, and here's 0. Put 0 down. Just do it. Trust. And then K is right here. 0.042 equals KC. So, the reaction will proceed. This is how you say it in the magic words. The reaction will proceed in the reverse direction until it reaches equilibrium because Q is greater than K. You have to say all of that. So you say the reaction will proceed, fill in the right direction until equilibrium is reached because Q is greater than K or Q is less than K, whichever one is relevant. Okay. So again, with this one, I would say the reaction will proceed in the reverse direction because Q is greater than K until it reaches equilibrium. How do you feel? It's not the worst thing ever. This in and of itself is not hard, but what's going to happen is you're going to be given this stuff and you're going to start making an ice table, and then after you've wasted 3 minutes, you're going to realize that you have no information to put a change or anything on the equilibrium sign, and this ain't really necessarily what you started with, so you don't really have anything for an ice table. Sometimes they will say initially blah blah blah, this is what you have, but still initially won't be at equilibrium, so you'll still make it Q. How are you guys feeling? Happy time so far? All right, so this is what they did, and then again, yeah, fine. And this is what I had said, but number lines. People stink, and I'm not being funny, I mean this. People stink at the little alligator signs, the inequality symbols. If you're not good at making alligators, y'all know what I'm talking about. If you're not good at alligators, then why don't you just write less than or greater than, and then not miss. I had somebody last year and they lost their stuff because they had written the inequality sign on the test and they did it wrong repeatedly. So that was sad. Don't be that kid. Like, just write less than or greater than. How about that? Y'all good here? Feeling good about this? All right, so what we're going to do is go to the document that I had attached for you, and it's called, like, I don't know. I don't remember what it was called, but something about equilibrium 2 practice or example. Sure. I wanted to make sure y'all understood this, so go ahead and do A and B for me, just to make sure y'all have it, because there wasn't another example for you to do on your own. So do A and B on your own, and I'll be waiting for you. You can do it on the whiteboard or you can do it on your paper. I don't care. Do you see on part B that they give you concentrations, and even though they say initial, doesn't say equilibrium. So that's how you know that you're not making an ice table. You're just you're gonna make a Q expression. have this in front of them? Probably just need to put it in the recycling bin. All right, you guys finished? No? Well, if you're still working, I'm going to go ahead and just kind of quietly start writing my solution up here, and then you can check your work. You done now? Yeah, sorry. I'm gonna go over that. So, anybody have trouble writing the equilibrium expression? That's your free point, right? Unless you forget that solids and liquids don't go in there, and then you lose your free point, and then you mess up the rest. Just kidding, but anyway, Q is where you're gonna just put into the equilibrium expression at some other point than equilibrium, and you know Q can be at equilibrium. So if we had done all this math and we had gotten 5.7, then we could have said, hey, it's at equilibrium. Okay, so. You fill your values in, then put it on the number line. Q is greater than K. So here's my justification. You have to say all these things, okay? Just like you have to say not only more electrons, but it's more polarized, blah, blah, blah. Like there's a line of things you have to say, and this is part of it. So anyway, the reverse reaction will proceed until the system reaches equilibrium because Q is greater than K. That's what you have to say, and that's what I wrote. I just ran out of room. Yes, sir? So, did I get it? I mean, did anybody else get 13.9? You got 13.9? So, what you have to do is you have to use a lot of parentheses. So, what you would do is you would take 0.538 times parentheses 0.993 to the third power, close parentheses, hit equal sign, divided by parentheses 0.215 times 1.76, close parentheses, equals. Lot of parentheses, a lot of hitting the equal sign. If you're ever not sure, hit the equal sign. That's the answer. A lot of times people will try to keep stuff going in their calculator like over and over and over again. And sometimes it's better to break it up. Like I break that up in half. Like do this part, hit equals, and then do the bottom half. But you'll get better at that. How we doing? Did you get it yet, Devin? Yes? Okay, good. Alright, so now that we've seen kind of what it looks like, what we did today, let's look at one that kind of goes back to what we had done on Friday. Oh, we have a little bit more. I'm just kidding. We are going to do one that's more like an ice table kind of setup here in a second, okay? Alright, so LeChatelier's principle is probably the easiest thing that we do in this unit. I mean, it's not probably, it is. So, a couple little tricky things that might get you, so I'll make sure I talk you through that. When a system is subjected to stress, the equilibrium is shifted in order to reduce that stress. It's great if you know his name. If you know his name is LeChatelier. But you can't put on the AP exam when they say to justify your answer or to explain. You can't say the equilibrium shift towards products because LeChatelier. You can't do that. So you might as well forget his name. It doesn't matter. You can't use that as a justification. Okay, so that's a common thing that I saw last year and that other people see. So if we're talking about gases, if pressure on a system at equilibrium is increased, so gas pressure, right? That's what we're talking gases. The equilibrium will shift toward the side with a fewer moles of gas. So let's take a look at that. So if I'm looking at this reaction, just look up here. Don't look at the picture yet. I have 2 N2, so that's 1 mole of gas. This is 1 mole. 3 moles of gas. So over here on the reactant side, I have 4 moles total. And on the product side, I have 2 moles total. So, remember Boyle's law? Boyle said that if I reduce volume, you increase pressure because it was PV equals PV. And so when you multiply things, they're indirectly related. Flashback Monday. Anyway, so if I reduce the volume and increase that pressure, what's going to happen is the equilibrium is going to shift towards the product side because fewer moles of gas. Now, if you're asked to make a reference to Q versus K on these, what would Q have to be to shift toward the product side? Greater or less than? So if you had, and you would understand that like if Q was 2 and K was 7, that would shift toward the products. And so if you're asked this, and it said a system with the gases, the pressure is increased, what will happen to the equilibrium? You would say that it would shift toward the product side because there are fewer moles of gas and Q is is less than K. So that Q and K thing, it may be on the key of where they're grading you, and it may not be. So it's just good to make a reference to it. And if you just think about it on a number line, you can use your common sense to figure out which way it's going to go, and then you use a number line to figure out Q and K. See how they match? Less moles of gas, but also Q is less than K. All right. And just for fun, remember it's products over reactants, right? So when we're making these Q versus K arguments, you can think about that mathematically. If I need to make more products to get to equilibrium, would I not have to make more products to get to equilibrium? Then the K would have to be bigger because it would have more products when it reaches it. So I'll kind of keep doing this over and over again with the math and the number line and LeChatelier, and then hopefully, like magic fairies, will land in your head. No, I'm just kidding. It does take a second to sink in sometimes. So if I decrease pressure or if I increase volume, it's the same, because sometimes on the AP exam they'll say you increase the you increase the volume of the cylinder. That would be the same as decreasing the pressure, right? So let me show you that. If I increase the volume, see how this is bigger than that, that is decreasing the pressure. So if I decrease the pressure, the system will move toward the greater moles of gas. Okay? And so in this case, Q is greater than K because at equilibrium, when it gets to equilibrium, it needs to make more reactants to get to equilibrium. So again, this number is going to be bigger when I get to equilibrium, which would make K smaller because I'm dividing by a bigger number. You don't get math, you can do a number line, right? Can you use your common sense to say that it will shift toward less moles? This way is shifting toward reactants. Q is less than K. I'm giving you like 3 options there. Of course, they're going to give you a bunch of circles to look at because it's not enough to know the math and the number line and LeChatelier. You have to look at circles too. So here, they might, not even give you which way it's going to go, or they might not even give you the reaction. Like what they would probably do is they would give you the picture and they say which reaction goes with this, or what situation, and you would have to figure out, what would fit. But you can kind of look at this and you can see that in this diagram I have more ammonias, the NH3s, and in this one I have more of the reactive products, reactive particles, the H2 and the N2. Can you kind of see that? So you can tell that the equilibrium shifted toward the reactants, these guys, because I have diatomic molecules instead of the ammonias. It's always about counting circles. All right, moving on. Y'all okay? All right, so this is probably the easiest one. If you increase the concentration of something, then it's going to shift away from it. And again, it's going to do that until Q equals K. So let's take a look at that. Oh, and by the way, I don't know if you've been noticing, the equilibrium constant, the KEQ or KC or KP, that only temperature changes K. Do I need to sing this song for you? Only temperature changes K. So that is only changed by temperature, but we are making temporary shifts until the equilibrium is reestablished. But the rate of the forward and reverse reactions at equilibrium will still equal, and K doesn't change. All right, so at equilibrium, this was the question from your homework, right? Okay. And it had 6 pictures, and it said, which picture shows the system at equilibrium? Did you do your homework? Do you remember that happened? And the answer was 5 or V. And so here's the deal. 5 and 6 had the same number of circles of each kind. So that tells me that the concentration of the reactants and products was remaining constant, which tells me that V was where equilibrium was reached. And so here I can tell the system is at equilibrium because I have the same concentration of each. So if at equilibrium, if I add more ammonia, you can already tell me probably, I hope, that the system will shift towards the reactants because Q is greater than K. So if I add 5 more ammonias, then you'll see that the equilibrium is going to shift towards the reactants because Q is greater than K. There's your little number 9, Q, K, going that way. That's it. If you decrease concentration, equilibrium is going to shift towards the side that you've removed the substance from. So here, at equilibrium, if I remove 7 ammonias, I'm going to shift toward the product sign because Q is less than K. Can you kind of see it in your head now? Cool. If you dilute something. All right, so on this situation, if we were doing concentration, okay, we were doing molarity, I mean, you can kind of see these little ions in your head. This is going to come into play huge next unit. Huge. So you'll appreciate this more later, or maybe hate me, I don't know. But if I dilute this, solution, equilibrium is going to shift toward the ions to make more ions. So if you think about this being you know, if each of these concentrations were 0.02 molar, and that's 0.02 moles in a liter, but then I double the volume, now it's going to be 0.01 molar, and so it's going to shift to make more of those. There's a lot more to this, and it's its own chapter in the old textbook. It's put in with acid base in this. Yeah, this is a whole chapter. So don't stress too much about this. Ha ha. Well, you can stress it, but you have to understand it's going to shift toward the ions, okay? Because it's going to try to dissociate more and make more ions. So anyway, stress from change in temperature. This is hard if you're lazy. Isn't all of life though? So let me just do this real quick for you. What they're going to do is they're not going to say plus heat. Like if plus heat's over here, then it's exothermic, right? So that means my enthalpy would be like negative something. Let's just say it's negative 42. They're going to give you this reaction, and then they're going to give you that little triangle H, that delta, that change in enthalpy, and then you're going to have to know if it's negative, then heat is a product. How you feel? Now you're going to treat it just like any other reactant or product. Okay? So let's just say that I changed the temperature. Let's say I heated this up. Heat is a product. So it's going to shift toward the reactants. That's Q is greater than K. Whatever. Now, this is actually going to change the equilibrium constant as well because temperature changes K. Now, what if they had given me the enthalpy of this reaction? I know it's not endothermic, but let's just pretend that it was. If they had given me the enthalpy of this reaction was positive, 16. Well, I guess you need to take your pencil and write in, just like it's a product or reactant, heat. Well, what if I cooled this second reaction down? What if I cooled it down? Wouldn't it shift toward the reactants to make more heat? If you don't take the 3 seconds to write the word heat on the right side, you'll get these wrong every time. But if you write it down and just pretend like it's sodium chloride or something, you'll be all right. Just trust me. Draw a number line, write the word heat, take your time. All right, so you add heat, it's going to shift away from heat. If you cool the temperature, it's going to shift toward heat. Okay, so here's kind of some more work that we had done, similar to Friday's work. So on this one, we actually don't need, let's talk about this for a second. A chemist mixes 80% nitrogen and 20% oxygen by moles in a vacuum and finds that the total pressure is a 1 atm at 25 degrees Celsius, and the Kp is 1.0 times 10 to the negative 30. So find the initial partial pressure. At any point, does he say that up here, does it say that he was at equilibrium? No. This is initial stuff, right? So he mixes it together, and that's where he starts. So find the initial partial pressure. And then on B, it says find the equilibrium partial pressure at 25 degrees Celsius. And I'm going to apply this back to what we just talked about today. So we're going there, but not yet. So find the equilibrium partial pressures at 25 degrees. So I'm going to have to do some math and get the first row of my ice table, because that's where I'm starting. This is where I started. And then it's asking me to find equilibrium, right? So this is an ice table. That's the difference. Okay. Anyway, if I have 80% nitrogen and 20% oxygen and the total pressure is 1 atm, then I guess I have 0.08 atms and 0.20 atms. Can you do that math? You'd have to show that math. So let's just go ahead and do it. Into O2. So you'd have to go 1 atm times 0.80 equals 0.80 atms of nitrogen. Then of course really the first thing I'd want to do is I'd want to write the equilibrium expression. Now these are partial pressures, right? So I'm going to use rounded parentheses. So Kp is equal to the bounce equation was it NO that it made? Is that right? Oops. All right, so I'm going to go ahead and let you guys calculate the equilibrium partial pressures of each. The Kp is so small that we can negate the minus x's and all that. Good times. Looking at the Kp value, the equilibrium concentrations of nitrogen and oxygen, which are reactants, do you think they'll be larger, smaller, same? If the Kp was one constant, the negative, gonna be probably not going to, probably not gonna make a whole lot of NO, right? Your Kp, remember, a little to the left, gonna remain pretty much same here. If you've been in eights, you should write out all these exponents. Yes.
Are those supposed to be in brackets?
Right here?
Yeah.
Yes. No.
So,
Thank you. In my defense, I wouldn't have lost points for that. You'd have lost them here, but still, thank you. You're right. How'd that go for you? Even AP Environmental Science, this next little discussion will be really interesting to you, hopefully. You may need more time to figure out equilibrium concentrations. It's important that you get x is equal to 2 times 10 to the negative 16. If you're not getting that, that means you don't know how to use your calculator right. Which is, I'm not being ugly like I'm going to help you, okay? Need more time? So, the chemistry of this is kind of cool. I like how when things actually relate to the world. This is room temperature. Don't check your brain out. Make sure things make sense. This is room temperature. This is atmospheric pressure normally. These are the two gases in the atmosphere at their pretty accurate percentages. 79% nitrogen and 21% oxygen, right? Alright, so anyway, if I put those in a vacuum, I would expect them to remain mostly their diatomic molecules. Nitrogen monoxide is a respiratory irritant, especially the young, old people with asthma, and it's a precursor to photochemical smog. And if you recall, do you remember how we talked about acid rain? And I was like, the heat from combustion takes the nitrogen in the air and oxygen in the air, and it makes nitrogen oxides. I feel like I said that a lot in the environmental science. But anyway, check this out. If the temperature increases a lot, like, I don't know, an engine or a power plant, the Kp goes up to only 2.5 times 10 to the negative third, from negative 30. So that means I'm going to get a little to the left, so if a larger number, I'm actually going to, I'm going to create more NOs. So, what you would have to do in this situation, if we use this, we'll have to use a quadratic formula, so we're not going to do that. But is this an endothermic or an exothermic reaction? If when I increase the temperature, the Kp goes up. So talk to your friends. Think about it in the terms of LeChatelier. And I'll fix that. Devin, do you think this is endothermic or exothermic? So you think that the heat is over here? So, okay, if this exothermic heat would be a product, right? So if I increase the temperature, which I did, from 25 to 2027, if I increase the temperature, then that would mean the reverse reaction would be favorable. So if my Kp goes up, the larger the Kp, the more the products are favored, a little to the left. So if the Kp is small, reactants are favored. If it goes up, then products become favored. So really, is it exothermic? So it's endothermic, and let's think about that. So this is the reaction. The enthalpy of this reaction is probably, the the temperature needed to make this go through is probably pretty high. The delta H is probably, I don't know, 300 or 400 kilojoules per mole. I don't really know. It'd be interesting to look it up, right? But it's probably high. So if I increase the temperature to that, that means I put in more heat, and then I see that the products start to be favored because the Kp has increased. So it's not just good enough to say, okay, if I put heat in it, it's going to go to the right because Q is less than K. But also, if you're given a Kp value that's new, you'd have to be able to mathematically think that through too. Is that okay? You get it? That's like a long stretch of like discussing this, but it is what it is. So remember again, the larger the K value, the more the products are favored. Alrighty, let's keep moving through this. Did these things. Yeah, we did it. Okay, and then they, at the new Kp value, they used the quadratic formula. I can do this. I did it when I was taking my class. And when I went to training, like, I actually did one of these on the board because nobody could remember how to do it, and I was sitting in that class at that point in my life. But you don't need to be able to do this. But if you do this, like on some tests, if you happen to need to do this, you're going to get the positive x will be the correct answer. You'll get a positive and a negative one, and the positive x would be the correct answer. Because you're not going to have, when you put in the negative one, it won't work out. Whee! All right, so, and you can tell here, if we had done the math with the new Kp value because it was a little bit larger, you can see there was actually a change in the pressures mathematically. Okay, so on these, I'm just gonna go to my whiteboard because I don't really like how they do this. So I scare myself when I switch over to the blank screen sometimes. I'm just like, did I just teach that? I feel like that sometimes. So here's a reaction. A plus B gives you A. Let's say the K value of that was 4. Now, what's going to happen is you're going to remember all the things we did with thermochemistry and combined reaction with Hess's law, and you're going to want to do those things. So the equilibrium expression for this would be AB over AB. If I reverse this reaction, my friends, so look, this is 4, right? If I reverse the reaction, if I reverse it, guess what happens to this little, guess what happens to this? This was basically 4 over 1. Doesn't all that become this? Yeah. If you reverse a reaction and you're talking about the equilibrium constant, you don't just make it negative. No, that's wrong. Super wrong. No. This is awesome dividing and multiplying stuff. Okay. So if you reverse a reaction, you take its Kc, put over 1. 1 divided by that. So reverse reaction, you take the reciprocal of it. How do you feel? All right. So let's say that I combine this reaction with another reaction. You know how sometimes you have to like add them up and all that stuff? Yeah. Anyway, super excited about it. Let's say we had A plus A. That doesn't even make sense, but whatever. I don't care. I guess I should make up new letters. I can do better. I'm better than this. What are other letters? E, F. That's good. A, F, and E. So, you know, you would like, this is a fun game where you like add things up, you know. And then you got some pigs and cows or that E-I-O over here. I'm starting to doubt my life as far as like, all right, does that all work?
Oh, okay. Now I get it. Yeah.
What did I do wrong?
On the product side at the bottom, it's AB and AF.
Oh. I'm gonna fail AP chemistry. Alright, whatever. So, you know with enthalpies, the delta H's, you would add these up. You would add up the delta H's. Well, guess what? Your equilibrium expression now is brackets AB, brackets AF, bracket E, divided by A, brackets squared, B, bracket squared, EF. And that ain't going to work anymore because you're multiplying all this stuff together. Do you understand that all these, listen to me, you listening? All these products are going to be in brackets to get multiplied together, and all these reactants are going to be in brackets to get multiplied together. You understand? So, guess what? If the K for this one was 0.01 and the K for this one was 0.02, your overall K now is not, it's so tempting to be like 0.03. Doesn't that seem, that's wrong. Okay, you have to multiply them together. And so 1 times 10 to the negative second times 2 times 10 to the negative second is 2 times 10 to the negative 4. If you don't know how to do scientific notation or have that fast, you have a problem starting in about 3 days, because they're doing the calculating on this, and we're about to get to a lot of these. But do you understand that 0.01 times 0.02 is 0.0002? You good? Yeah. So you multiply together, because when you add up reactions, you end up having to multiply their concentrations. And then the last one, I know everybody said, please make it stop. And then the last one is if I have A plus B gives me AB. If I multiply all this by 2, like if you know how sometimes you double the reaction. Well, guess what? The old equilibrium expression was this. Right? That's the old equilibrium expression. But now the new one is that. So guess what? You have to do the old KC value was 5. It's not 5 times 2, it's 5 squared, because everything is raised to 2. So this is really easy, but you have to think of it. Are you okay? I'm going to take you to their PowerPoint now. I have to explain it in my words and then use this. This is not even simple enough for me. Alright, so look, don't freak out. Everything's cool. This is the original equilibrium expression. 2A's plus B, 6D's. That's the original. Well, if I reverse it, you can see that sucker gets flipped upside down, so take the reciprocal of it. See it? No worries. If you add these up, like I was showing you, you end up having to multiply all their equilibrium constants together. So when you add stuff up, you multiply. Basically, take whatever you think, knee-jerk reaction, and take it to that next level. If you feel like, oh, I should add it up, multiply it. If you're like, oh, I should multiply it, raise it to the power. If you feel like you should reverse the sign, then flip that thing upside down. Okay? That's all I got for you today. So I'm going to let you take the answer key. And then